Dakshita Khurana, who unfortunately cannot be here with us today. Dakshita came down with a flu-like illness and a high fever a few days ago. Initially, she postponed her Monday flight to Tuesday, hoping to arrive here at 4 a.m. today to be in time for her talk. But unfortunately, her fever returned and to her and her family, so making it impossible for her to travel. But fortunately, with the remote setup here, she will be able to join us online. So let me now introduce Dakshita. So she is an associate professor in the Department of Computer Science at UIUC, and also a scientist at NTT Research. She received her PhDs from from UCLA in 2018. She was a postdoc at Microsoft Research, New England, and started her assistant professorship at UIUC in 2019. So Dakshita has done great work in many topics in the theory of cryptography, such as secure computation, non-malleable cryptography, proof system, and quantum cryptography. So in particular, recently she has done many fundamental works in the recent exciting development of quantum cryptography and its connection to quantum complexity theory, which you will hear about from her today. And she has published more than 40 papers at IACR conference, as well as many papers in leading conferences in theory and the quantum community. She was invited to speak at top quantum conference venues such as Qcrypt and TQC, and gave a long plenary talk at QIP. She also serves as steering committee member at Qcrypt and constantly serves as PC members in crypto and theory conferences. So it is our pleasure to invite her to speak at the Asiacrypt 2024. And the title of her talk is The Complexity-Theoretical Foundation of Quantum Cryptography. So without further ado, let's welcome our speaker. Hi, Dakshita, can you hear us? We cannot hear you.
Can you hear me now?
Yes, we can hear you. Yeah.
Okay, great.
Great.
Thank you
Do
so
you want
much.
to show your slides?
Let me see. Let me make sure I can share.
Okay, we can see your slides.
Let's see. I think I need to switch the.
Yeah, good now.
Okay, great.
Okay, thanks. Please.
Yes. Thank you so much, Kai-Min, for that introduction. And I'm really, really sad that I was not able to make it there in person. I came down with a nasty virus, and that made it impossible for me to travel, despite trying quite a bit. It's really special to be asked to give this talk at Asiacrypt. Exactly 10 years ago at Asiacrypt, I gave my first conference presentation. This was back in Kaohsiung, Taiwan, and Asiacrypt has ever since held a special place in my heart. Without more ado, let me get started. I'm excited to tell you all about the complexity-theoretic foundations of quantum cryptography. And a lot of my own work that I will talk about in this talk is based on joint work with Kabir Tomar, who's my student at UIUC. Sorry. Okay, so let me just start out by saying that the holy grail for all theoretical cryptographers is to try to build cryptography without making any unproven assumptions. A huge obstacle to this task is that secure classical cryptography can exist only if P is not equal to NP. So if you want to build crypto without unproven assumptions, we need to at least prove that P is not equal to NP, which is a very tall order. In light of this very difficult obstacle, an updated dream is to maybe try to build cryptography while only making minimal unproven assumptions. And it's been well known for a while now that in classical cryptography, this minimal assumption is the existence of one-way functions. Um, and and I'm sure that everyone at at an ISCR conference is familiar with what a one-way function is, so I'm not going to go back and describe it. But you also may be familiar that this problem of whether one-way functions exist or not has ruined many a cryptographer's sleep for decades. It's a very hard problem. And it's even harder than proving that P not equal to NP in some sense, because proving that may not suffice to actually establish the existence of one-way functions. And in fact, there's this beautiful five worlds interpretation by Russell Impagliazzo, who define these different potential realities that we may live in, depending on whether P equals NP, or perhaps P is not equal to average case NP, and so on. And I'm not going to go back and define all of these worlds. I just want to emphasize that there are two worlds called minicrypt and cryptomania, which are the ones where cryptography can exist. So in particular, minicrypt is a world where one-way functions exist. Mini, as in small, crypto can exist, but advanced public key cryptography cannot. And then cryptomania is this world where one-way functions exist, but also public key encryption, multi-party computation. And these days, we know from lattices really advanced primitives like functional encryption and obfuscation and so on. So, and understanding which reality we actually live in remains an open question. Now, given the number of difficulties and obstacles that we've been faced with in the classical setting, a very natural question is to try to understand what happens in a quantum world. And in particular, it is famously known that quantum key distribution is a type of cryptography which enables distributing keys over untrusted channels. And this is achievable without having to make any unproven assumptions. But of course, as we all know, cryptography is not just about key distribution. For example, we as a community care about, and for good reason, care about commitments, multi-party computation, signature schemes, public key encryption schemes, and so on. And what do we know about the existence of these primitives in a quantum world? Well, for quantum commitments and MPC, just like quantum key distribution, commitments and MPC secure against computationally unbounded adversaries were actually believed to exist. So it was believed that commitments exist that remain secure against unbounded adversaries without having to make any unproven assumptions. And see, for example, remarks in some of these works. And then Crepeau and Killian proposed a template to build MPC based on the existence of such commitments. And so this was all well and good, and people thought that not only QKD, but also commitments, MPC, all of that is much easier to do in a quantum world. You don't need to study complexity theory to do it. You don't need to make assumptions and so on. However, a few years later, there was a proof that commitments against unbounded adversaries are completely impossible in a quantum world. So this was in independent works of Mayers and Low and Cha. And this basically blew this area wide open again. And it became open again to try to understand what assumptions do we need to assume in order for secure computation and commitments and so on to exist. And there was some recent progress here, and in particular in a work with Bartosek, Coladangelo, and Ma, and in a concurrent work of Grillo, Lin, Song, and Vaikunthanathan. And then this was improved in a subsequent work of Anant, Kian, and Yuen. It was basically shown that if one-way functions exist, then commitments exist. This was known. But basically, if commitments exist, then secure computation can exist in a quantum world. Now, as you may already have noticed, this is remarkably different from a classical setting where one-way functions or commitments are known to be impossible. It is known to be impossible to build secure computation from one-way functions or commitments in a classical world. And yet, if you had quantum capabilities, and in particular participants were able to send quantum states to each other, then surprisingly, one-way functions are good enough to get all the way to secure computation. Another really interesting recent result has been building public key encryption with quantum public keys, so quantum variations of public key encryption from one-way functions. This was done in these two recent concurrent works of Baruti et al. And Kitagawa et al. And again, this is something that is provably impossible if you just had classical keys. So if you look at a quantum world, we already know that if one-way functions exist, you don't need more advanced structure from lattices and so on. If post-quantum one-way functions exist, and you have participants that are quantum capable, then they will be able to actually realize multi-party computation, public key encryption, and so on, which is really classically completely impossible. So this is sort of the first, or after QKD, the first evidence that that in a quantum world, the amount of hardness that you need in order to build cryptography may be different than the classical setting. Now, great, so one-way functions suffice to do these complicated cryptographic tasks quantumly, but then a natural follow-up question is, can commitments or quantum cryptography or MPC in general be based on assumptions that are weaker than the existence of one-way functions? And why is this even a question? Like, why do we even think this is possible? Well, in this really beautiful work of William Kretschmer back in 21, he showed that relative to a quantum oracle, there is this quantum primitive called a pseudo-random state that can exist even if BQP equals QMA. So you should think of BQP and QMA as the quantum analogs of the complexity classes P and NP respectively. And so what this and then another subsequent result showed is that relative to oracles, there exist hypothetical oracle worlds where P equals NP or BQP equals QMA, and this object called a pseudo-random state can exist. Again, a pseudo-random state is a quantum relaxation of a pseudo-random generator that we all know and are familiar with. And it turns out that these pseudo-random state objects imply commitments. So what all of this is saying is that commitments can exist in oracle worlds where P becomes equal to NP or BQP becomes equal to QMA. And in fact, it has been conjectured in this recent work of Lombardi, Ma, and Wright that relative to a classical oracle, commitments can exist even if all problems that can be classically described can be easily solved. Sorry, that third author there should be Wright, not Wicks. Which means that there's a strong possibility that quantum cryptography can be based on assumptions that are mathematically weaker than one-way functions, and in fact, assumptions that may hold even if P equals NP. In other words, an adversary that has access to an NP oracle will not necessarily be able to break these assumptions. This is very unlike all the assumptions that classical crypto relies on, which do break given access to an NP oracle. Okay, so this is great. There is this beautiful promise that, you know, in oracle worlds, it's possible that you could use hardness that is much, much harder than NP hardness to realize quantum cryptography. And I want to again emphasize, you know, that there is this, the very first works to realize something like this were these two concurrent works of Anant Kian and Yuen and Morima and Yamakawa that showed that pseudo-random states imply commitments. So what is a pseudo-random state? It's a primitive that maps a classical secret onto a quantum state such that the output state is computationally indistinguishable from what is called a Haar random state. And like I was saying before, think of this as very similar to a PRG, a pseudo-random generator, except that the output is not a classical string, but a quantum state. Okay? And in a construction that closely mirrors the Naur construction of commitments from PRGs, it was shown that pseudo-random states can give commitments with quantum commit messages. Okay, so before moving on, I want to point out that not only pseudo-random states, but on this slide, you can see a lot of other quantum cryptographic primitives that have emerged in recent years that are implied by one-way functions, but can potentially exist even if one-way functions do not exist. And in fact, there's many more primitives. You can go to Orsatat's graph and check out some of the, he has a pretty large list of quantum crypto primitives that and the relationships between them. And so while we explore this land of quantum cryptography that may exist even if P equals NP, I want to draw your attention to some questions that I think should guide the research that we do as theoretical cryptographers in this area. So one question that intrigues me is there a quantum analog of one-way function? So one-way function is the central, minimal, really important primitive in classical cryptography. Is there a quantum analog to this assumption? Some other questions that I want to discuss a little bit later in this talk are what hard problems should we base our quantum crypto systems on? And third, what connections does quantum cryptography have with complexity theory? So let me first start out by trying to understand this question better. Is there a quantum analog of one-way functions? And to understand it, I want to start out by discussing what quantum one-way assumptions look like. What are some assumptions that we've already studied? The first is a quantum computable one-way function. So this is exactly like your standard notion of a one-way function, except computing the function requires a quantum computer and not just a classical one. Okay, so this is really just a one-way function, but where f is quantumly computable. Another one-way quantum assumption that people have looked at and studied is what is called a one-way state generator. This was introduced in this work of Morimi and Yamakawa, and they defined it as a quantum efficient algorithm that maps a classical secret to a quantum state such that given many copies of the quantum state, it's still hard to extract the classical secret. So this is again, very similar to a one-way function in that given the output, it's hard to find the input, except the output is not a classical string, it's a quantum state. This is a very natural primitive because if you look at signature schemes and encryption schemes and so on, where the hard task is to find some type of classical secret given a quantum state, then these primitives will imply a one-way state. This was shown in this work of Morimi and Yamakawa. And so this is a really natural relaxation of a one-way function that we should look at. Excuse me. Another relaxation is what is called a one-way puzzle. So let me define that now. A one-way puzzle models a quantum process that samples hard on average problems along with their solutions. So this is an efficient quantum sampler that outputs pairs of strings x and y that satisfy some relation such that, given y, it is computationally intractable to find a pre-image of y satisfying the same relation. So I want to emphasize here that the relation is not necessarily an NP relation. This is going to be important to us a little later on in the talk. So again, I want to say that if the sampler was classical, then it is without loss of generality for the relation to be an NP relation. Then this object is exactly a one-way function. But if you have a quantum sampler, then this is not necessarily a one-way function, and the relation is not necessarily an NP relation. Okay, and so so far we've looked at quantum computable one-way functions, one-way states, one-way puzzles. Let me also tell you just a little bit about one other, one-way quantum object that you could define that is different from all of these. This is called a state puzzle. So this captures the hardness of synthesizing a quantum state given a public identifier. In other words, there is an efficient quantum sampler again that outputs a pair, but now one part of the pair is a classical string S. This is going to be the public part. And the hidden part, the one that is going to be difficult to find, is a quantum state, get psi S. And the hard task, like I just told you, is given the string S, it is hard to output a state that overlaps with the hidden quantum state, get psi S. This is interesting because, for example, because it is implied by other crypto primitives that appear in the wild. For example, quantum money is a primitive that is important in quantum cryptography, and it implies this object, this state puzzle object. And I also want to say that I also want to contrast this with a one-way state, where in a one-way state, the challenge is a quantum state, and the hard task is to find a classical key. Whereas with a state puzzle, the challenge is a classical string, and the hard task is to find a secret quantum state. So these are, opposites of each other in some sense. Okay, so you could define all of these different one-way primitives and try to understand the relationships between them. I'm going to really quickly tell you some of the relationships that we know. So quantum computable one-way functions almost completely immediately imply one-way states. It's trivial. One-way states with pure outputs imply one-way puzzles. This was shown in this work with my student Kabir. One-way puzzles, on the other hand, imply commitments and MPC, which means that one-way states, one-way puzzles, and so on are useful, and they do give commitments and MPC, which are cryptographically important and useful primitives. And moreover, in a more recent work, we showed that one-way puzzles and state puzzles are equivalent to each other. So, recall that in a state puzzle, the task is to find a secret state. In a one-way puzzle, the task is to find a secret string. And we showed that these two tasks are actually equivalent. And I also want to mention this independent work of Kian, Reyes, and Zandri, which also showed directly that state puzzles imply commitments and MPC. So in summary, these are all of these notions of one-wayness are useful, and they imply commitments and multi-party computation. Okay. Another thing I want to say about one-way puzzles is I want to bring your attention to this relaxation called a distributional one-way puzzle, which was introduced in this work of Chung, Golden, and Gray. And it captures the hardness of distributionally inverting a puzzle. In particular, again, there's a sampler which efficiently outputs X and Y pairs, such that given Y, now the hard task is going to be to sample X distributed according to the output distribution of the sampler, conditioned on the string Y. So if you're familiar with distributional one-way functions, this is the same thing, except applied to one-way puzzles instead. This work of Chung, Golden, and Gray also showed that distributional one-way puzzles are actually equivalent to one-way puzzles. And so just coming back to our, placing of all these different one-way primitives, I would maybe want to say that of all these, it seems like one-way puzzles is implied by everything else and is also useful. So this could be considered a reasonable quantum analog of a one-way function. And moreover, its distributional version is equivalent to the standard version, which is something that we're going to use moving forward in this talk. Okay, so with that, I want to wrap up, the first part. And this is all I had to tell you about quantum analogs of one-way functions. Now I want to use again this one-wayness lens of looking at the complexity of quantum cryptography and try to say a little bit about how we can base quantum cryptography on some hard problems that are different and are harder than the problems that we base classical cryptography on. So in the second part of this talk, our goal is going to be to try to understand if one-way puzzles can be based on mathematical problems that are harder than problems in NP. So problems that will remain hard even if P happens to be equal to NP, for example. And again, just to quickly remind you, what is a one-way puzzle? It's a quantum process that samples hard on average problems along with solutions. So there's a sampler outputting X and Y strings such that given Y, it's computationally intractable to find X, satisfying this relation R. And our goal is now to build one-way puzzles from hardness beyond NP. So what do I mean when I say hardness beyond NP? We could look at this graph of complexity classes where the complexity class P is, at the small red circle at the bottom there. And this is the class of all efficiently decidable languages. And then we go outwards into NP, which is the class of efficiently verifiable languages. And then beyond NP lies the polynomial hierarchy, beyond which lies P to the sharp P, P space, and so on. And while one-way functions lie in NP, so these are average case versions of problems in NP that have that are efficiently sampleable. What we will see is that one-way puzzles will lie all the way up in P to the sharp P. So we will build one-way puzzles from problems that are conjectured to lie outside the capabilities of the polynomial hierarchy and within P to the sharp P. And we'll see that very shortly. But I want to just emphasize here the contrast between one-way functions as a complexity assumption and one-way puzzles. Okay, so let me now move on. The main theorem that I'll tell you about for the next few minutes is in this more recent work with Kabir, where we showed that under certain conjectures that have been widely studied in the quantum advantage literature, one-way puzzles exist if and only if P to the sharp P is not equal to BQP. So that means, just going back to our graph here, if there's any problem in the blue region, P to the sharp P, that's not in the orange BQP region, then one-way puzzles exist under certain conjectures. Okay. So let's proceed, and let me tell you a little bit more. Our goal is to try to build one-way puzzles from the mildest possible assumption. What can this be? Well, the first thing to note is that one-way puzzles are invertible by a sharp P oracle, which means that if P to the sharp P were equal to BQP, so if efficient quantum computers could perform all sharp P computations, then they would be able to invert all one-way puzzles, and one-way puzzles would not exist. That means for one-way puzzles to exist, we require, at the very least, we need to assume that P to the sharp P is not equal to BQP. This is due to a work of Cavalier et al. So now can we go ahead and base one-way puzzles only on this really this minimal assumption that P to the sharp P is not equal to BQP? This is the goal that we initially set out with. Our dream was to build quantum crypto from just the fact that sharp P is not in BQP. Now, let me tell you what sharp P is. Sharp P is a counting complexity class, which captures the complexity of answering how many satisfying assignments does a given Boolean formula have. The canonical sharp P complete problem is the problem of computing the permanent of a matrix. So what is the permanent? I have an example written out for you, but people are often more familiar with the determinant. And a permanent is simply the determinant, but without the minus signs. So you just add everything up instead of subtracting alternating terms. Computing the permanent of a matrix is known to be a sharp P hard problem in the worst case, and actually also known to be sharp P hard in the average case for many nice distributions over matrices. So this is a problem that comes with a worst case to average case reduction for free, which is great news always for cryptography, because we're looking for average case hard problems. And our goal was, well, let's try to build quantum cryptography from the hardness of computing permanents of random matrices. Sorry. Okay. So a big bottleneck that showed up as soon as we set out is the following. Our goal is to build a one-way puzzle, and recall that a puzzle sampler needs to efficiently sample XY pairs where given Y, X is hard to find. Now let's just do simple pattern matching. Our hard problem is given a matrix A, its permanent is hard to find. So let's set X to be the permanent of a matrix and Y to be the matrix itself. And pattern matching says that given Y, X is going to be hard to find. Great. So are we done? If you read the first line again, it says the puzzle sampler needs to efficiently sample these X and Y pairs. which means we require some distribution over matrices for which it is easy to efficiently sample pairs of matrix and permanent together, such that given the matrix, the permanent is going to be hard to find. And this actually turns out to be pretty hard. And in fact, we think that it is unlikely that for natural distributions over random matrices, it's unlikely that there is an efficient, even quantum sampler that's going to be able to sample these matrices together with their permanents. Well, so that means this is not great news. We were stuck for quite a while. We almost gave up. And then we started looking at this really beautiful literature on sampling-based quantum advantage. It's been studied in various different models under the name of boson sampling, random circuit sampling, IQP, and so on. And if you've heard, the recent Google announcements, you must be familiar with the words random circuit sampling. If not, don't worry. Let me just tell you real quick. The idea in all of these experiments is that quantum circuits can efficiently sample from certain distributions such that the probabilities of outputs of these distributions, these are distributions over classical strings, where there is a quantum sampler sampling from these distributions, and such that the probabilities of particular outputs encode the permanence of certain unitary matrices. So what this work does is relate the problem of computing permanence to the problem of computing probabilities of quantumly samplable distributions. In particular, just making it more explicit, if permanence of these unitary matrices were hard to compute, then that means the probabilities of outcomes of these distributions are going to also be hard to compute. Why is this any more helpful? Let's see. Let's try to use this fact to build one-way puzzles. Recall that we just said that the hard task now is computing probabilities. In particular, there is a distribution over classical strings such that for some random classical string A, it is going to be hard to compute the probability assigned by the distribution to the string A. Great, so once we have this type of hardness, can we set our x and y pair to be the probability assigned by the distribution to the string A along with A? So meaning y, which is the challenge, is the string A, and the value that is hard to find is this probability assigned to the string A. And we know that, given A, it's hard to compute probability of A, so maybe this is fine. Turns out that this suffers from the same problem. We need to be able to efficiently sample x and y pairs, whereas this, again, is hard to sample. It is easy to sample from the distribution capital A, but it's hard to sample a string A together with the probability assigned to it. Okay, so all that is easy to sample is the string A. A, comma, probability of A is hard to sample as before. And so this is not great news. However, using some indirection and using this really nice result on distributional one-way puzzles implying one-way puzzles, we can get around this problem. In particular, the following is a distributional one-way puzzle. Take our distribution capital A over strings, sample a string from this distribution, say that the string is n bits long, sample a random index from 0 to n minus 1 to truncate. This indicates a length to which we will truncate our string. And now y is simply going to be the first I minus 1 bits, or the first I bits of our string, and x is going to be the next bit. So my claim here is that given a random truncation of a string sampled from the distribution, the next bit of the string is hard to sample. And let me give you, an oversimplified reasoning for why this is the case. In particular, recall that we want to argue that as long as probabilities are hard to compute, this one-way puzzle is indeed a distributional one-way puzzle. We'll do this by contradiction. So given an adversary that on input a random prefix of a string A samples the next bit of the string perfectly, we will build a reduction that will be able to approximate the probability assigned by the distribution to any particular string in its support, up to small errors. For example, suppose we have such an adversary that's sampling next bits perfectly, and we would like to use this adversary to approximately compute the probability assigned to some string A. Let's say the string A is 0, 1, 0, 0, blah, blah, blah. Okay. What we will start out by doing is we will run the adversary on the empty prefix many times and look at the probability that the adversary outputs first bit 0. Call that P0. Next, we will run the adversary on the 0 bit many times and estimate the probability that the next bit output by the adversary is 1. And now we'll set P01 to be the product of P0 and P1 given 0. Next, we will run the adversary on prefix 01 and approximate the probability that the next bit is a 0. And keep going this way bit by bit, multiplying the estimates we get each time, and this is actually going to give us the probability of sampling the entire string 0100. Okay. So hopefully you all see that given an adversary that on input, a random prefix of the string perfectly samples the next bit, it is possible to build a machine that approximates every probability assigned to every string up to small errors. Now, it turns out that if you have a distributional one-way puzzle inverter, basically an adversary that breaks your distributional one-way puzzle, then it's not always going to perfectly sample the next bit. It's going to be allowed to make errors. And so it only samples from a distribution that has some inverse polynomial statistical distance from the correct distribution. These errors are a pain to deal with, but it turns out you can deal with them. I'm not going to be able to get into the proof here, but turns out that what you can say is that even in the presence of these errors, one can build this machine B that will approximate these probabilities on average. So for most random strings A, we will still be able to get probability of A up to small errors. And so that means if we assume that quantum computers can efficiently sample from a distribution such that probability is assigned to strings in support of that distribution are hard to approximate and not always too tiny, then this is sufficient to build one-way puzzles, which in turn give quantum cryptography. Now, this assumption, why is this reasonable? It turns out that this is implied by conjectures that have been studied for decades in the literature on sampling-based quantum advantage. In particular, boson sampling is this really nice experimental setup that uses linear optical arrays to sample from certain distributions that classical computers cannot sample from. And there they conjecture already that permanence of random matrices with N01 Gaussian entries are sharply hard to approximate on average. Sorry. Similarly, random circuit sampling is this setup where you set up a random quantum circuit, and it is conjectured that the output probabilities of these circuits are sharply hard to approximate on average. And similarly, IQP is another model of quantum circuits. And so all of this long line of work has already studied and found evidence supporting the conjecture that these probabilities are extremely hard to compute, not just NP hard, but actually sharp P hard, and not even to exactly compute, but to approximate. Okay, so in other words, our assumption, the only assumption that we need is that for a quantumly efficiently samplable distribution, approximating these probabilities is impossible for efficient quantum machines. Why do we believe this is the case? Because, well, this is believed to be a sharp P hard problem, and we don't believe that efficient quantum machines can solve sharp P hard problems. I also just want to quickly say that, we don't expect this assumption, this problem, to imply one-way functions, because if you could use efficient classical or even quantum reductions to build uh, a one-way function, or in other words, if you could use efficient reductions that, I'm sorry, let me say that again. If you could build efficient reductions that used any one-way function inverter to solve this problem, then we'd be solving sharp p-hard problems in much lower levels of the polynomial hierarchy, which we believe should not be possible. So this is why we believe this problem to be a much harder problem than inverting one-way functions, which is good for cryptography because the harder our problem, the more secure our crypto system. Okay, so let me now just say a little bit about this section. To summarize, it turns out that one-way puzzles, state puzzles, and commitments can be based on random circuit sampling / boson sampling / IQP, all of these conjectures from the quantum advantage literature. And so these are like solid mathematical problems that people have looked at, and they do imply quantum cryptography. I want to leave you with a question related to what I've just said, which is, what about other quantum cryptographic primitives? So not just commitments, but there's other interesting things that we want to do in a quantum world, like signatures, public key encryption. I already told you pseudo-random states were an important and interesting primitive. Can we build those from concrete mathematical problems for which there is evidence of hardness, which is, independent of the existence of classical cryptography? In recent months, there's been some progress on these problems. In particular, people have looked at certain quantum circuit architectures and analyzed underlying assumptions that would give rise to a variety of quantum crypto primitives. But as far as I know, building them from assumptions that are, independent or provably independent of the existence of classical cryptography is still very much open. Okay, so with that, let me now move on to the short final part of my talk, where I want to say a little bit about what connections does quantum cryptography have with complexity theory. So I want to start out by saying that traditional complexity theory, not just classical, but also quantum complexity theory, considers the problem of deciding languages where the instances are classical. So even these complexity classes like QMA or QCMA that you may have heard of, that are quantum analogs of NP, have instances that are classical, but maybe the witness is quantum or the verification is quantum and so on. Now, on the other hand, quantum cryptographic tasks, for example, the task of breaking a quantum protocol like a commitment, cannot be neatly framed as classical instance problems. And really, the instance now is quantum. And this requires like a new type of complexity theory then that would study unitary transformations or transformations for problems that take quantum states as input and perhaps generate quantum states as output. This has been studied in some recent works, one by Bostanci et al., the other by Lombardi, Ma, and Wright, and a more recent work by Chia, Chung, Wang, and Shi. And I think that this is a really important and useful direction. But in this talk, I'm going to say just a little bit about how even our traditional understanding of complexity theory can say a little bit about quantum cryptography and vice versa. Sorry. So to do that, let me first start out by saying, recall we started off by looking at Impagliazzo's 5 worlds, and there's been some efforts in recent works to define what quantum analogs of these worlds would look like. And here is my own, really feeble attempt at this. The first is that, it started out by observing that if one-way functions exist, or like in mini-crypt, but with quantum resources, you can actually do multi-party computation, quantum public key encryption, signatures, commitments as before, and so on. And so mini-crypt is pretty powerful in a quantum world. But also, you don't actually need one-way functions to exist in order to do a lot of interesting crypto, like commitments and MPC, just require, well, not require, but it is sufficient for one-way puzzles to exist if you wanted to do commitments and MPC. And so there's this word that was defined, this word that was first coined by Tomoyuki Morime called microcrypt, which is a world where one-way puzzles, this is a world where commitments and MPC exist, but one-way functions do not necessarily exist. And if you frame this as a world where one-way puzzles exist, then you would at the very least require that p to the sharp p is not equal to bqp in this world. So these are, two possible realities that we could be living in. But there's also some additional possibilities that I want to draw your attention to. One is, a world where one-way state generators and other efficiently verifiable primitives exist. So quantum public key encryption, signature schemes, and so on are examples of primitives which are characterized by efficient verification algorithms. And it's you could imagine worlds where one-way functions do not exist, but these other efficiently verifiable quantum primitives exist. And then one other world that is interesting to look at is a world where quantumly computable one-way functions exist, but classically computable one-way functions do not. And in this world, it is necessary that QCMA is not equal to BQP. And one of the really good consequences of quantumly computable one-way functions existing would be that we would have quantum cryptography with classical communication. So these are, again, some attempts at understanding different realities we could live in. And there's been some really nice recent work separating some of these worlds from each other. So for example, in three really nice recent works, Chen, Colodangelo, Sadat, and then follow-up work of Bostanchi, Chen, and Nehoran, and Behra, Malavolta, Morime, Moore, and Yamakawa showed unitary oracles that separate one-way state generators and quantum one-way functions from one-way puzzles. Another really beautiful recent work of Kretschmer, Kian, and Tal built classical oracles separating one-way functions from quantumly computable one-way functions, meaning that classically computable one-way functions are all broken, but quantumly computable one-way functions still exist. And then another work of Golden, Morimai, Mutreja, and Yamakawa gave unitary oracles separating quantumly computable one-way functions from classical communication primitives. And so there's been some really nice activity on separations. And I want to go back to this figure and show you, what this means is that one-way puzzles, so there are worlds where one-way puzzles exist, but none of these other efficiently verifiable primitives to the right of them exist. There's also worlds where quantumly computable one-way functions exist, but classically computable one-way functions do not, which basically means separations between the first, second, as well as the third and fourth worlds. Of course, as you can imagine, it is open to try to understand how the two worlds in the middle relate to each other. I would suspect that there's again a separation in the right, going from left to right. So meaning that there should exist oracles relative to which potentially one-way state generators exist, but quantumly computable one-way functions are all broken. I'm not familiar of an oracle separation proving this, but maybe yeah. Correct me if I've missed someone's work later. Okay, but as far as I know, this is open, but should be true. And also the question mark to the extreme left of the screen is just indicating that we don't even understand whether p to the sharp p not equal to bqp, is necessary for the existence of quantum commitments. So there could be other worlds to the left where, let's say, one-way puzzles do not exist, but quantum commitments and MPCs still exist. And that's also something that that remains an important open problem. So with that, let me just end with a few more open problems for you all. The first, can we further weaken assumptions for commitments? So like I was saying on this slide, on the extreme left, is there another world on the left where commitments exist, but one-way puzzles do not? We don't know. This is related to the unitary synthesis problem, where one version of it that we don't know how to answer is, can we efficiently implement every unitary if P equals P space? Or every efficiently describable unitary, let's say. Another open problem that I'd like to understand is, what is the relationship between quantum advantage and quantum cryptography? In particular, the ability to do quantum cryptography without relying on classical hardness assumptions or post-quantum hardness assumptions, the standard ones, seems to imply some form of quantum advantage. So really, these two seem, highly related to each other, and I think I think trying to understand this question will shed light on the assumptions that we can base quantum cryptography on. And finally, when can we extract computational/cryptographic hardness from physical processes? So for example, it turns out that random circuit sampling and other quantum advantage experiments are a very fertile source of cryptographic hardness. And are there other physical processes that we could extract such hardness from? These are just some questions. I'm happy to answer any other questions that you may have, but with that, I'd like to summarize. With that, I'd like to end. Thank you.
Questions?
Thanks for nice talk. So could you go back to our new one? So Michael could be main cube.
Yes, 1 second. Sorry, I'm going to try to play again. Just a second. You wanted me to go back one slide, right? Is this?
Yes, this slide. So you mentioned we don't know separation EV cubed and main cubed. So mean Q cubed. But I think can we separate by using Kretschmann oracle? So you suppose you have exponentially many how random unit is for P space complete ranges as an oracle. So in that world, Kretschmann shows BQP equals QMA, so which means BQP equals QCMA. So therefore, we can say in that or relative to that oracle, quantumly computable one-way function do not exist. But in that world, so pseudo-random unit exists, we can say one-way series exists. So its oracle is separate EB-crypt, Q-crypt, I think.
Yes, you are absolutely right. Yes, thank you. Yes, so Kretschmer's original oracle should separate the second world from the third one. Yes.
Yeah, thank you.
Thank you. Thank you for pointing that out. Yes.
More questions?
This is a very naive question. You mentioned the relationship between quantum advantage, like sampling-based quantum advantage, and quantum public key cryptography. So far, all claims of quantum advantage have been challenged by classical algorithms that claim to solve the same problems. Is this pointing to flaws in the experiments, or is this challenging the assumption you had on your slide on the separation between the classical and the quantum world?
Right. So, so the way that that's a good question. Thank you. So the way that claims of quantum advantage have been challenged by classical algorithms that achieve the same sampling task is because of noise. So in particular, it's known that if you assume certain noise models on your quantum sampler, then there are classical samplers that will sample from the same noisy distribution. What we are doing here is assuming an idealized version. So we actually don't say anything about, noise in the quantum sampler. So that's, I think, a very orthogonal question, I think, to what we care about here. In particular, the experimentalists care about demonstrating quantum advantage using an actual noisy quantum computer. And on the other hand, we are assuming that you have ideal error-corrected quantum computing. And it seems like, we're getting closer to it with really amazing breakthroughs in error correction that have been happening as of late. But yeah, our assumption is, ideal error corrected quantum computers exist with no noise on their output. I do believe that we should be able to modify these crypto systems to make them resilient to some amounts of noise without necessarily breaking them, but that is not what we do here. I hope that answers your question.
Yes, yes.
Are there more questions? Oh.
Thank you for your talk. Let us consider the following analogy. In classic computations, in classical cryptography, we never base our concrete schemes on NP hard problems. Actually, it seems to be even impossible. Please correct me if I'm wrong. We always make a relaxation of such problems. And that gives us a mechanism how to base a crypto system on NP hard problem using the relaxation. In your talk, you mentioned the relaxation of random circuit sampling and boson sampling. Can it be used in construction of certain security assumptions a crypto system can be based on?
Right. So maybe I'm going to attempt to answer the question, but please correct me if I misunderstood something. So one of the analogies that I was trying to draw here is that while classical cryptography requires problems that are in the complexity class NP, they're not necessarily NP hard. And like you said, we actually don't believe that they're NP hard, but they are in NP and hopefully not NP. Whereas here, one of the insights was that we could rely on problems that are in P to the sharp P, and that actually have previously been conjectured to even be P to the sharp P hard. But let's even say that they're not. They're still, we do believe that they lie outside of NP, so are harder than NP hard problems, or sorry, harder than problems in NP. And so and that is a good thing because we are trying to say that quantum cryptography can be based on problems that are much harder to solve than all of our classical problems. And so I don't know if that addressed your question, but I just wanted to point out, this distinction between problems in NP versus problems in sharp P.
It almost answers my question. My question was whether that distribution approximation trick can be used in a manner akin to relaxation of a problem, so we can instantiate such schemes efficiently in practice.
Great. So unclear. I don't have a very good intuition for how efficiently these schemes will work in practice. So it's this is more of a theoretical result, trying to understand the theoretical basis for quantum cryptography. Yeah, so I'm not sure.
Thank you very much.
Thank you.
So it's about time. We can take final quick question, if any. So if not, so Dakshita, we actually prepare a certificate of plaque to you. But since you are not here, we will mail it to you later. So thanks again. Let's thank the speaker again.
Thank you so much.
Okay, so now track switch.